And this talk is called From Undersea Cables to Maxwell's Equations. And if you don't know what Maxwell's equations are, you probably won't be much wiser when I've finished, but I'll do my best. So at the 2022 AWA conference, I gave a talk on cable versus wireless, where I laid out the 120-year history of the interaction of cable and wireless from the early 1900s through today. And neither of them won, as it turned out, although cable's doing pretty well at the moment. But anyway, I'm not going to cover that period. But before that, there was already another 50 years of cable history, and also many developments in electrical theory. In 2021, the AWA's Houck Award for Documentation was presented at the conference to Bruce Hunt for his book Imperial Science, Cable Telegraphy. Oops, come on. Let me get in here. There we go. Imperial Science, Cable Telegraphy and Electrical Physics in the Victorian British Empire. In the book's 300 pages, the author examines the rise of the submarine cable industry from its beginnings in 1850 and describes in detail how solving its many technical problems led to the involvement of scientists such as Michael Faraday, William
hear that one?
Fleming Jenkin, and James Clerk Maxwell. Their work, together with that of other scientists and many cable engineers over the next 50 years, resulted in... Who's talking? So anyway, for the next 50 years, the result was a network of telegraph cables that reached almost every part of the developed world by just after the turn of the century. And this is a map of the Eastern Telegraph Company's system and its general connections, which if you look at a map of today's internet connections, is about the same. A lot more in the Pacific now, but otherwise the world is circled by cables, as it was then. In this talk, inspired by Bruce's book, I'll show how the cable industry, which was an entirely commercial enterprise that made, laid, and operated the cables, and they collaborated with the scientists to the benefit of both commerce and electrical theory. We begin in 1850, when the design and operation of ocean cables was a whole new technology with almost no theoretical basis. The first international undersea cable was laid between England and France in August that year. And that little cable there is just 1/4 of an inch diameter, and a piece of copper in the center and gutta percha, and they laid it about 22 miles across the English Channel. This cable was made to a deadline, and it had no exterior protection. They didn't have time to put any armoring on it, and they weighed it down with lead weight so it wouldn't float. But as a result of laying this cable and getting it to work, at least briefly, they secured the franchise from the French government. All they had to do was transmit a few messages in each direction, and they got a monopoly on connections from England to France. And this was the Submarine Telegraph Company. So this cable failed quite quickly, mainly from abrasion on the rocks off the French coast. But they came back the next year, and what a difference. This almost looks like they went forward quite a long way. This cable is fully armored. It's got 4 conductors, and you can see the graphic there of its design with the copper cable, the gutta percha insulation, hemp and jute packing, and then iron armoring wires for protection. And that one they laid in September 1851, referred to as the Dover to Calais cable. And this was the first ever commercially successful undersea cable. And this design and construction established principles which persisted for really about 100 years. This is an original factory sample in the diagram. Now, making a cable isn't simple, and they didn't really know that at the time. So I have only a couple of slides I'm actually going to read from, but the mechanical requirements are fairly straightforward. You had to source thousands of miles of copper. You had to source gutta percha for insulation and iron wire for the armoring. You had to manufacture and test the cable core, the copper plus the insulation. You then had to armor it. Then you need to splice it, since you made it in shortish lengths and had to splice them together. Then you had to store it so it didn't cause any problems before you were able to lay it from heat or improper storage. You needed machinery on board ship to pay out the cable at an optimum rate, and you needed grappling tackle and a hauling engine to recover it in the event of a fault. And finally, specialized ships for laying and repairing cable. And they didn't really know most of this in the early days. The electrical requirements were even more complicated. There was no such thing as pure copper in the early 1850s. So you had to work out how to get the copper refiners to refine it better so it could be made into wire with a decent quality. You had to specify the number and size of wires in the conductor and the optimum composition and thickness of the gutta percha insulation, both of which had a great influence on the ability of an undersea cable to carry information. You needed to measure the precise electrical characteristics. You wanted to achieve the maximum traffic capacity, and you had to reduce something they call retardation, the signal delay on long cables caused by creating an electric field underwater. And in the event of a problem, you needed instruments to find the accurate location of a fault. So the progress was initially quite slow. The landline telegraph's been successful with just poles in the ground and almost any wire form in the circuit. And they'd already proved their worth with financial and business transactions. And the cable pioneers hoped they could achieve similar success just by insulating the wire. And this was achieved by the late 1840s using gutta percha, a thermoplastic tree resin found mainly in Malaysia. Gutta percha had been introduced to Britain in 1843, whereas the first thermoplastic, it found ready applications where you wanted to mold something. Before that, there wasn't really any way to make anything out of plastic. You had to machine it or make it out of wood, or that was about it, really. So these are examples of gutta percha from the 1840s. In 1848, Michael Faraday saw gutta percha, and he suggested it would make an excellent insulator. This was his first contribution to cable science and technology. And at this time, Britain had an effective monopoly on gutta percha, which served the cable industry very well for almost 100 years. It wasn't superseded until polyethylene was invented between the wars and not made available for cables until the late 1940s. It's almost 100 years of gutta percha. However, while it did make a gut insulator, the attempts to transmit signals across the English Channel in 1850 showed that cable telegraphy was not so simple. Rather than Morse code, the proprietors used a printing system to record plain text on a paper slip at the receiving end. This was very forward thinking because nobody had done that before. But unfortunately, while some intelligible messages were exchanged, enough to prove the successful operation of the cable and secure the franchise, other messages were garbled. This was the first experience of what came to be known as induction, which caused what they called retardation, or delay of the pulses of the signal, and also stretched them out, causing them to be hard or impossible to discriminate at the receiving end. So if you send a dot, you get the effect where you charge a capacitor and it slowly discharges. And if you sent a dash right after it, it would kind of merge together. And unless you transmitted them at a very slow speed, you couldn't discriminate them when you're receiving them. They also found a little bit later that long underground lines suffer from the same problem, but far less, which meant they had to be worked at a lower rate, reducing the amount of traffic they'd be carried and hence the revenue. In 1852, this phenomenon was studied by Latimer Clark, a young engineer with the Electric Telegraph Company, and they were planning to lay both underground lines and subsea cables. He tested the transmission of pulses through 100 miles of insulated wire immersed in water and 175 miles while stored dry, and found that while there was no delay in the reception of the signal through the dry wire, the current, he said, took a very perceptible time in traveling the 100 miles of the underwater wire. He also recorded the received pulses using chemically treated paper moving under stylus and found that the dry signal made well-defined dots and dashes, while the wet signal showed the dots and dashes merged into an unreadable line if sent at any speed. And unfortunately, none of that tape survives to show its exact results, but it's fairly clear what was happening. And in fact, to us, it's obvious that this effect could be easily demonstrated by putting a capacitor across the line. Latimer Clark came to a similar conclusion, comparing the insulated wire laid in water to a Leyden jar, in which the charge from the battery induced an equal and opposite charge on the outside of the gutta percha insulation, which took some time to build up and thus resulted in the delaying of the signal. Latimer Clark had no solution for this problem and did not publish his results at the time. Meanwhile, back in the 1930s, Michael Faraday had produced an electric current by moving a coil of wire near a magnet. Faraday was self-taught, and with no grasp of mathematics, he instead visualized lines of force around a bar magnet and also around a wire carrying a current. And he came to call this the electromagnetic field, I think the first time that term was used. Faraday's theories didn't receive much attention at the time, but he continued his research. Meanwhile, in October 1853, Latimer Clark repeated his 1852 experiments with Faraday, who he hoped could help address the retardation problem. Clark also performed further tests with Faraday and the Astronomer Royal, George Biddle Airy, who had encountered problems when trying to use the telegraph for determination of longitudes. And the problem with longitudes is you need to know the exact time between 2 points, and one of those points would be the Greenwich Observatory, which is 0. And in order to measure the precise longitude, you need the exact time. So telegraph cables and later undersea cables would have been ideal for that if you could get a signal through them. Latimer Clark had already told Airy the bad news about retardation, which would prevent the exchange of accurate time signals, but he wanted Airy Biddle to see the effect in person. To show this, Clark used underground lines between London and Manchester, which is about 200-mile distance, and he looped them together to form a 1,600-mile circuit, which clearly demonstrated the effect of retardation to Faraday, Airy, and several other telegraph engineers. The astronomer Royal did further tests on a circuit between Greenwich and Brussels in November and December 1853 with similar results, and in January 1854, he made the first published mention of the effects of induction in an article in the Athenaeum magazine. More importantly, Faraday gave a lecture at the Royal Institution later that month, in which he provided a comprehensive description of how retardation and distortion of the signal were explained by his theory of the electric field, and how the extent of the effect depended on the dielectric surrounding the conductor. In the case of a cable, the dielectric was the gutta percha, which was sandwiched between the copper conductor and the iron armoring wires, plus a large extent of seawater, which was the problem, of course. For an overhead line, the dielectric was simply the surrounding air. Faraday thus showed the importance of what he called the specific inductive capacity of different dielectrics, which had a great influence on the transmission of a signal. He also noted that the informal collaboration between philosophers, such as himself, and those who put the theories into practice led to new facts and new results. So this was really the first statement of the importance of collaboration between the practical guys who were running the cable and the scientists who were trying to figure out why all these things happened. So the great attention paid to Faraday's lecture led to physicists and engineers taking further interest in his electric field theory. Perhaps the most significant of these men was William Thomson, then a 29-year-old professor of natural philosophy at Glasgow University, who, as Bruce Hunt notes, would become one of the towering figures of 19th century science. Of particular interest here are his contributions to cable telegraphy, which made both his reputation and his fortune. Later in 1854, Thomson published papers which confirmed Faraday's theories. These showed the results of his own approach to the calculation of the electrostatic capacity of telegraph cables, and he filed a patent for improvements in electrical conductors for telegraphic communication, the first of many patents that he filed. He also began a correspondence with James Clerk Maxwell, then a 23-year-old advanced research student at Cambridge University. Maxwell, too, became interested in Faraday's field theory, and in December 1855, he published the first of many papers that would, quote, transform the foundations of electromagnetic theory. All this happened within just a few years and marked the beginning of the development of a formal field theory over the next several decades. Encouraged by questions from other scientists, William Thomson himself considered his research into the propagation of signals across telegraph cables. In October 1854, in a letter to George Gabriel Stokes, a distinguished Cambridge mathematical physicist, Thomson presented a simple equation which defined the rise of current and potential at the far end of a submarine cable. From this, it could be shown that the retardation of a cable would be proportional to the product of its resistance and capacitance, and thus the retardation would increase with the square of its length. This was really bad news, of course, because if you're looking for long cable and you've got a square factor problem, you're in trouble. While this law of squares, as it became known, explained why the problem became much worse on longer cables, the solution it suggested was impractical. Increasing the size of both the conductor and the gutta percha insulation would reduce the retardation, but would also result in a far higher cost of materials, which would increase even worse with the cube of the length. Thomson's theory was published in May 1855 in the Proceedings of the Royal Society, accompanied by a graphic which are called arrival curves. These curves were derived from his equation and illustrated in mathematical form the effects that Latimer Clark and others had observed when sending a current pulse across a cable, an initial rapid rise in the waveform, followed by a long tail as the pulse moved through the line, and a substantial delay in observing the maximum value at the receiving end. So we're now getting into really formal studies, detailed experimentation, careful notation of results, and publication. This, of course, also explains why Morse code dots and dashes, simple pulses of equal amplitude but different lengths, could not be distinguished when sent over a long cable. Bruce Hunt in his book notes that Thomson's work on this subject was clearly coming to touch on some of the deepest questions in electrical physics. And here we are really just 5 years into laying cables and first observing these effects. By the end of 1855, 25 cables had been laid, not all of them successfully, and the issue of telegraph retardation had not only become of importance to the operation of all submarine cables, but was also doing much to set the course electrical physics would follow in Britain over the next decade or more. And these early cables were all short connections. They were only just starting to think of an Atlantic cable. And these ran around the British Isles, parts of Europe, and short connections between the UK and Europe. And meanwhile, in North America, the British-born telegraph engineer Frederick Gisborne had been attempting to erect a telegraph line across Newfoundland with the intention of reducing the time taken to get messages between the financial centers of Europe and America. And this is the proposed line from St. John's all the way across Newfoundland. And then he's looking to get a little further with it. So his plan was to have mail ships drop off containers they passed St. John's on the right-hand side of the map there, and then telegraph the messages to New York via a series of landlines, a short cable between Newfoundland and Nova Scotia, and then the railroad telegraph landline down to Boston, New York, and Washington. And that would reduce the message time by several days. So if you put a letter in the mail, it might take 3 weeks to get to New York. If it was dropped off at Newfoundland and sent down, it would only be a little over 2 weeks. However, that whole section of Newfoundland is basically impenetrable. The area on the right-hand side, the east side, is where most of the habitation is today, and then along the coastline. But the interior is pretty tough to get through. So Gisborne was faced with the difficulties of raising poles and running wires across his interior. And by late 1853, he'd run out of funds. So he went to New York and he met there Matthew Field, who suggested that he speak to Cyrus Field, a wealthy businessman who was looking for someone new to engage him in the hope that Field would invest in Gisborne's project there. Field wasn't initially interested, but it's said that while looking at his large floor globe, which is now at the Smithsonian, he was struck by the idea of continuing the connection across the Atlantic. Field was a paper merchant who was semi-retired in his early 30s, and he knew nothing of telegraphy and couldn't anticipate the possible difficulties that might be encountered in laying a 2,000-mile cable 20 times longer than any presently in operation. However, he talked to Samuel Morse and Peter Cooper, and he also got assurance from the naval oceanographer Matthew Fontaine Maury that recent soundings of the bed of the North Atlantic would be ideal for supporting a cable. And so Cyrus Field decided to go ahead. And there's the route he's proposing. So there we are on the west end now at St. John's again, or that part of Newfoundland, with New York still 1,000 miles away. And the line would go across the Atlantic and land at the little island of Valentia on the west coast of Ireland. From there, the signals could go across Ireland on a landline, across one of those short cables from Ireland to England, and then by landline down to London. That was the easy part. That 2,000-mile bit in the middle was going to prove tricky. So in April 1854, Field and his partners took over Gisborne's franchise in Newfoundland, and they formed the New York, Newfoundland, and London Telegraph Company. And the first step was to complete the landline across Newfoundland. As Gisborne had found, this proved quite difficult, and it took over 2 years to lay that line across Newfoundland. In 1855, while the landline was in progress, Field visited Britain for the first time to order a cable to connect Newfoundland and Nova Scotia as part of his proposed Atlantic cable route. He arrived in London in early 1855 and met with John Watkins Brett, whose submarine telegraph company had laid the 1851 cable across the English Channel. And there they are. Field ordered 75 miles of cable to be shipped to Newfoundland, and that's the section to connect Newfoundland to Nova Scotia across the Cabot Strait. And an attempt was made to lay that in summer of 1855. There were difficulties with the vessels used, one of them being towed by the other, which possibly wasn't the best idea, and the cable had to be cut and the expedition abandoned. Field, however, was undeterred, as he would be for the next 11 years. He ordered a new cable from England and laid it the following year, in 1856, without incident, and by now the landline was complete, and Field was ready to lay the main cable across the Atlantic. Unfortunately, by this time, the New York Newfoundland Company had run out of capital, so Field set out again to England in July of 1856, and with Brett, began looking for investors for a new company to set up in London. The Atlantic Telegraph Company was registered in October 1856 and raised £350,000 of capital, about $1.7 million at the time, and many tens of millions if you scale it to today's values. The company's prospectus made the bold statement that it is determined to complete and have the telegraph in operation during the ensuing summer. In other words, within just 10 months after the launch of the company, without having a cable made, ships, and any idea of what the technical issues would be. But as you might expect, the rush to complete the project resulted in many problems. With the knowledge now of retardation, including Thomson's theory that it would increase with the square of the cable's length, critics doubted that such a long cable could be made to carry enough traffic to make it commercially viable. Anxious to silence his critics, Cyrus Field engaged an electrical experimenter with a rather different theory, the splendidly named Edward Orange Wildman Whitehouse. He also enlisted the 22-year-old chief engineer of the Magnetic Telegraph Company, Charles Tilston Bright, and their Brighton Whitehouse. Wildman Whitehouse, he was generally known, was a surgeon by profession, but like many educated men of the period, he had taken up natural philosophy, as the study of various sciences was then known. In the early 1850s, at the age of about 35, he began the study of electricity with a particular interest in telegraphy. Through this, he too encountered John Watkins Brett, who was impressed with Whitehouse's investigations and in 1855 provided him with funds for equipment expenses. The telegraph field in Britain at this time was quite tight. I think everybody knew everybody else, and they were mostly friendly competitors. And Brett gave Whitehouse access to two recently completed cables at Cooper's factory in East Greenwich on the River Thames, which was a 6-conductor, 150-mile cable destined for the Mediterranean, and also to Field's 3-conductor, 75-mile cable, which would shortly be shipped to Newfoundland. Whitehouse performed many measurements on these two cables, whose conductors he connected in series provide a total length of 1,125 miles in his test circuit. In September 1855, he presented a full account of his experiments to a meeting of the British Association in Glasgow. As he had neither scientific credentials nor telegraphic experience, he began by justifying his status as that of an experimenter whose findings might aid practical progress at what was a critical time in the field. From his experiments, which of course were carried out on insulated conductors on dry land rather than underground or underwater, he found that strong alternating pulses from a magneto-electric generator showed much less retardation than did the usual battery current. He concluded that using pulses of this type, he could achieve signaling speeds over the 1,125 miles of wire that would be sufficient for commercial success. William Thomson, who was much more of a theorist and in fact was one of the major physicists of the 19th century, he didn't agree with Whitehouse's methods or conclusions, and he wrote about this at the time. He recommended instead that the performance of existing cables should be studied, noting that a 300-mile unarmored wire recently laid in the Black Sea had a signaling speed of only 5 words per minute. Thomson's law of squares, scaled up to the 2,000 miles of the proposed Atlantic cable, just over 6 times the length of the Black Sea cable, would result in a retardation 36 times worse, or a speed of only a fraction of a word per minute. Whitehouse, in turn, didn't agree with Thomson, and in August 1856 he presented a paper to the British Association titled "The Law of Squares, Is it Applicable or Not to the Transmission of Signals in Submarine Circuits?" His conclusion was not, of course, but after extended discussions between Thomson and Whitehouse by means of letters and papers in the scientific press, each conceded that the other had some valid points. Crucially, Thomson said he'd been too hasty in his analysis of the Black Sea cable's poor performance, which he now believes was at least partially a result of less than optimal sending and receiving instruments, and he calculated that the Atlantic cable should be able to transmit a single letter every 3.5 seconds, or about 3 words per minute, which would be commercially viable. And remember, the alternative to this proposed cable was putting a letter on a ship for 3 weeks and waiting another 3 weeks for a response. So even at a slow speed of transmission, the cable would be a valuable tool. This, of course, is exactly what the Atlantic cable promoters needed to hear, as they were launching their new company, and they added Whitehouse as a projector, or principal of the company, and appointed him as electrician. An electrician was the term for the highest office in the technical field. There were no electrical engineers yet, only electricians. and Whitehouse is now the electrician of the Atlantic Telegraph Company. In October 1856, a decision had been made on the design of the cable. Thomson's theory suggested a heavy conductor with thick insulation, while Whitehouse insisted that this was not required. Because of the deadline stated in the company's prospectus, there was not much time for testing and evaluation of cable samples. And even though Whitehouse later said he'd require 3 months for testing, only minimal testing was conducted, and Field chose a design for the core of the cable, the conductor plus the insulation, similar to that used on his Cabot Strait cable earlier in 1856. So again, they're rushing here. Here's the 1857 cable being manufactured. And you can see on the right a section that's been cut back to show the design. And that cable is just 3/4 of an inch in diameter at the blunt end. And it consists of 7 22-gauge copper wires, arranged 6 around 1, gutta perch insulation to a diameter of about 3/8 of an inch, and then jute yarn saturated with tar and beeswax, and the outer arming was 18 strands, 7 wires each, of number 22-gauge best charcoal iron bright wire. So those 7 copper cables, time two of them out, was 14,000 miles of copper, and the outer arming, instead of being a single wire wrapped around perhaps 10 or 12 sections, it was 114 wires, and they needed over 114,000 miles of iron wire as well. So this kept the wire drawing industry in Britain working for quite a while. And again, they were in kind of a hurry, which turned into a little bit of a problem later. In early December 1856, the Glasgow shareholders elected Thompson to the board of directors of the Atlantic Telegraph Company. And from then on, he became enthusiastic about Whitehouse's signaling system and equipment, including Whitehouse's high-voltage induction coils, which we'll run across again later. With the design of the cable settled, the manufacturer was contracted out. The Gutta Perch Company of London would produce 2,500 miles of insulated core. So in other words, they would take the copper wire and extrude the gutta percha around it. And then it would be sent off to 2 other companies to apply the armoring, Glass Elliott in London and Newell and Company in Birkenhead near Liverpool. While this is all going on, Whitehouse is beginning to work on the instruments and apparatus he would use to operate the cable. In April 1857, the board of the company authorized spending more than £3,200 to acquire sets of Whitehouse's patented batteries, induction coils, and relays. And it was later reported that in all, the company spent some £13,000 on Whitehouse's electrical department, about $60,000 at the time, and again, many tens of thousands of dollars today. After the cable was loaded on the 2 ships that would lay it, and it was coiled horizontally in what are called cable tanks, the sections were connected together for tests on July 30th, 1857. Whitehouse uses induction coils and relays to check signaling rates, and while he reported that the results were satisfactory, Samuel Morse, who was on board ship and observed the test, wrote to his wife that the speed was only 20 words in 16 minutes. The expedition continued regardless. They were kind of committed at this point. The many problems encountered in attempting to lay the cable in the summer of 1857 and the subsequent abandoning of the expedition are well documented, and I won't describe them again here. We only need to know that the leftover cable was returned to land and was stored in poor condition until the next year. Meanwhile, William Thomson had been doing some more scientific experimentation, testing the electrical properties of iron and copper wires. And when he joined the board of the company, he began measuring the resistance of copper wires made for submarine telegraph cables. And he noted that I was surprised to find differences between different specimens so great as most materially to affect their value in the electrical operations for which they are designed. He found that the conductivity could vary by a factor of 2 to 1 or more, which would of course affect the performance of a cable. His tests were too late for the 1857 cable, but when it came time to order cable for a new expedition in 1858, he made sure that the purity of the copper was included in the contract, the first time this had ever been done. So we're seeing here the collaboration starting to pay off, and that now the manufacture of the cable is going to become more rigorous. While Whitehouse was working on improving his huge induction coils and magnetic relays over the winter of 1857-58, Thomson was conducting his own investigation of a new signaling system, which resulted in the design and construction of his mirror galvanometer. And you can see how this works. You have a galvanometer with a very sensitive movement and a tiny mirror mounted on the coil, so that when it sees even the smallest signal, it twitches either left or right, depending on the polarity. And in order to magnify the result of that so you can see it, you reflect the light from a lamp off the mirror, and it comes back to the scale. And as you've seen, if you have a watch and you hold it in a sunbeam and flash it against the wall, you see how fast you can move the spot by moving your wrist a tiny amount. And this works on that principle. So you could get a reasonable deflection on the scale, maybe an inch or so from this tiny impulse coming in, but it meant you could read very small signals at the end of a long cable. So Thompson asked the company for £2,000 to complete the work on his instrument, but having spent so much on Whitehouse's gear, the company turned him down. This decision actually made Thompson a very wealthy man eventually, as he patented the mirror galvanometer and other key equipment, then charged the cable companies a substantial license fee for their use. He didn't sell the equipment to them. He said, you need this equipment, it's so much a year. Whitehouse's signaling system used a high-voltage induction coil up to 2,000 volts and receiving instruments of average sensitivity. But Thomson's mirror galvanometer could detect very small signals, and even on a long cable, a battery of only about 50 volts would produce signals readable at the destination. In late May 1858, the two ships of the cable fleet set out for a test of new paying-out machinery on the ships in the Bay of Biscay. Whitehouse was supposed to accompany the expedition, but said his doctor had forbidden him to sail, and Thompson took his place. Just before departure, Thompson took delivery of the very first marine galvanometer, a more robust version of the lab version, and placed it in the instrument room of HMS Agamemnon, the British ship of the fleet, amid an array of Whitehouse equipment. And that mirror galvanometer is on view in the Science Museum in London, a historic instrument among many others there. On June the 10th, 1858, the cable fleet set out to rendezvous in mid-Atlantic. There, the two sections of cable would be spliced. Agamemnon would steam for Ireland, while Niagara, the American warship that was loaned to the company, would proceed to Newfoundland. Another set of Whitehouse's high-voltage equipment was carried by Niagara and her escort ship, ready to be set up in the cable station at Newfoundland. After many mishaps at sea, the attempt had to be abandoned, but the ship set out again on July the 17th for a final try. And on August 5th, 1858, Agamemnon arrived at Valentia and Niagara at Trinity Bay, Newfoundland, and the cable was finally connected between Ireland and Newfoundland. During the voyage, communication had been maintained between the two ships over the cable, although not without some difficulty. And that process is followed today. Even on fiber optic cables, you start at the shore end and you connect the cable and you start paying it out. You take the onboard end of the cable and connect it to your instrument, and now you have full communication through the cable while you're laying it, which immediately shows any problems. At Trinity Bay, they had built a cable house, literally a house, and Charles de Sauty, who had supervised the electrical staff on board the Niagara, was now superintendent of operations at Newfoundland. They moved into this newly built cable station and began setting up Whitehouse's batteries, induction coils, and relays, which took several days. While doing this, they kept a steady battery current on the cable with slow reversals so that the Valentia could monitor the state of the circuit in Ireland. And you can see on the left-hand wall there, the heavy cable is coming up from the shore up to the cable house, in through the foundation and onto the test bench. And the smaller wires running up to the roof are the landline telegraph across Newfoundland, on which the signals would be relayed. You can't do a direct connection between the signals because the cable signal is too small to relay. So it would have to be read, recorded, and rekeyed in order to send it on. So there are almost no interior images of the Newfoundland station, but one of the cable operators, Theodore Linder, was an amateur artist, and he painted this watercolor of the telegraph room. And that's the only idea of how we had it set up. Also, this is the only view of Wildman Whitehouse's giant induction coils, which were close to 8 feet long. And you can see the bank of batteries on the table. Those will all be 1.5 to 2 volt cells in series. And then they jump this induction coil, and out comes 2,000 volts you apply to the cable. And you may wonder what effect that would have on the cable. As we said, it's only a small copper strand and 3/8 of an inch diameter of insulation. But a few years ago, some of my friends in England took a section of cable from the period and put it on a high voltage tester, and they ran it up over 20,000 volts without it failing, without the insulator breaking down or arcing across. So the cable design itself was good. But unfortunately, there was a different issue with the cable in 1858, which I'll go into in a minute. At Valentia, William Thompson, who'd be out on the Agamemnon, As they landed, he handed over the cable to Whitehouse, and the equipment was set up in a small building at the Slate Works in Knightstown, then the only town on the small island of Valentia. The building remains in place today, although derelict, and it's hoped to restore it as part of the joint bid for World Heritage Site status for Valentia and Heart's Content as a joint enterprise. It's to be a first in World Heritage Sites, where two parts of the site are 2,000 miles apart. The operators of the cable were supposed to use Whitehouse induction coils to send the signals and his relays to receive and record them on paper tape. At Trinity Bay, they discovered that the currents from Valentia were too weak to trip the relay, and Thompson had a similar problem at the Irish end, although De Sode in Newfoundland kept and certified a short section of tape marked First Current, 9th of August, 1858. And to my knowledge, this is the very first recording of the very first signal ever sent across the Atlantic by telegraph. And this came down in De Sode's family. His son certified it as genuine. It came down in the family from there. And Bill Holly ended up with it eventually. He was a major collector of historic cable things. And I bought his entire collection some years ago. So I'm very pleased to own this historic thing. But as you can see on there, the tape is marked with lines. And what they did, as they said, they received the signal by Thompson's mirror galvanometer and basically keyed it onto the tape, okay, so that Whitehouse could say, yes, his equipment was part of the circuit, which in fact, it really didn't work well at all. So at Valentia, the operators tried Thompson's mirror galvanometer instead of Whitehouse equipment, and they were able to decipher a message from Trinity Bay on August the 10th. Perhaps ironically, the message was, repeat, please. And in fact, many of the messages during the period the cable operated were, please send again, please send slower, send V's, which gave a repetitive pattern, repeat, please. So at Valentia, they set up a two-man system. One man would watch the spot of light on the mirror galvanometer, and the other would use a local battery and Morse key to transfer the message to paper tape. William Thompson then left Ireland for home, leaving Whitehouse in charge, and Whitehouse, unwilling to admit that his system didn't work, sent some of the tapes to the directors in London, occasionally describing them as signals first transmitted and received across the Atlantic by the company's instruments. Very carefully worded there. Another problem was that all was not well with the cable itself. As I'd mentioned, after the loss of a good length of the cable during the first unsuccessful attempt in 1858, it was found necessary to use some of the leftover 1857 coil on the second and temporarily successful expedition. This cable had been stored in adverse conditions and some of its insulation had been compromised. So even though my friends were able to run it up to 20,000 volts today, what had happened was that it was stored in the sun, coiled horizontally, and being thermoplastic, the copper wire had slowly sagged downwards until it wasn't far from the outside of the insulation. And with that reduction in the thickness of the insulation, the high voltage was able to break through it after it had been laid and Whitehouse was sending his high voltage coils. So despite the exchange of a limited number of messages over the cable, including greetings from Queen Victoria to President James Buchanan on August 16th, followed by a reply from the President to the Queen, and the Queen's message took 16 hours to transmit. It was a couple of hundred words. And the performance of the cable continued to be erratic. Ignoring instructions from London, Whitehouse ordered several sections of suspect cable near shore to be replaced, and also tried other measures, none of which proved useful. Finally, the directors fired Whitehouse for ignoring their orders, and on August 21st, William Thompson returned to Valentia, where he instructed the operators in Newfoundland to use his mirror galvanometer. While this proved effective for about 10 days, it was clear that the insulation of the cable was irredeemably compromised. There was one good point after this. Two final messages sent to Trinity Bay from Valentia on August 31st proved very important in supporting the declining reputation of the Atlantic Telegraph Company. These messages were sent by the British government to its regiments in Canada, cancelling earlier orders to sail from Canada to India to aid in putting down a rebellion. So the cable said, do not send the ships. And this saved the government about £50,000, about $250,000 at the time. So this was kind of a proof of concept. And even though the cable failed soon after, the company had shown that you could lay a cable, you could repair it to some extent, and you could get a signal across it. But by the end of 1858, the Atlantic Telegraph Company had abandoned the installation at Trinity Bay and returned all the staff to Britain. Meanwhile, the scientists are still at work. So William Thomson, together with Cromwell Fleetwood Varley of the Electrical and International Telegraph Company, continued investigating the condition of the cable at Valentia for several weeks. And their resistance measurement showed that the probable fault was hundreds of miles out to sea without possibility of repair. So now they're using the known resistance of the cable recorded during its construction to make resistance measurements and estimate how far a fault to the Earth or a fault to the seawater would be. And this was a valuable technique that they were developing. So, although much of the blame for the failure of the cable was laid on Wildman Whitehouse, just about everyone involved from Cyrus Field on down had been at fault in some way. William Thomson perhaps came out best of all, as his mirror galvanometer and the subsequent siphon recorder that he developed from it, which recorded incoming signals on paper tape. These became the standard instruments of cable operation, and his theory had been confirmed that the size of the copper conductor and the gutta-percha insulation were important design characteristics, particularly for long cables. So there were several issues that remained as to what lessons could they draw from this? How could they take advantage of this failure? How should future long cables be made and laid? And how should electrical phenomena be measured and understood? The answer to these questions proved to be the turning point in the development of not just the technology of cables, but equally important, the complex electrical theories behind their testing and operation. So remember now, we're only 8 years into this project after the first cable was laid, and what they've achieved is absolutely remarkable. And they're already thinking, well, how are we going to do the long cable and make it work so we can make a lot of money at it? And in fact, by 1860, over 11,000 miles of cable had been laid, and only a little over 3,000 miles was still working. And there'd been another expensive failure after the failure of the Atlantic cable in 1858. In 1860, a cable across the Red Sea as part of the India Line had failed, and the British government, as well as the leaders of the cable industry, agreed it was now most important to find a way to explain why so many cables had failed and to define principles and methods to assure the success of future cables. So in 1860, in collaboration with the Atlantic Telegraph Company, the British government set up a joint committee to inquire into the construction of submarine telegraph cables. That was its official name. And the 8 members of the committee were all well-respected men with expertise in every aspect of telegraphy. And these included both scientists and engineers. Among them were Charles Wheatstone, one of the inventor of the telegraph in Britain, Cromwell Fleetwood Varley, chief electrician of the Atlantic Telegraph Company, and Latimer Clark, whose achievements and investigations into cable issues I described earlier. The committee had 3 objectives: taking testimony from experts, collecting experimental studies, and drawing up a final report in which the committee members would consider all the evidence and lay out their conclusions. The company's first meeting was on December 1st, 1859, and in 22 sessions over the next 9 months, it took extensive testimony from witnesses involved in every aspect of cable making, laying, and operating, 43 of them in all. And then in 1861, the committee concluded its work and produced a 550-page official report, which was published that summer. And this is, give you an idea, this is legal size, 550 pages, fairly small type, and it's the most comprehensive analysis that I've ever seen of an electrical problem. The document began with 32 pages of conclusions and recommendations, the key statement on the many unsuccessful cable projects being, it will be observed that the failures of all these submarine lines are attributable to defined causes which might have been guarded against. So they basically said, you could have fixed this stuff, but you were in too much of a rush. So this was a cautionary note to the cable industry, who were still making money, but a lot of people lost a lot of money on the Atlantic cables. So this book includes 280 pages of minutes of evidence and analysis and 240 pages of appendices with the results of experiments carried out on behalf of the committee. The 18 appendices were perhaps the most valuable product of the committee, and among many other topics included these key contributions. So people had investigated these, the permeability of gutta-percha and inerupt water when subjected to high pressures, a study of the insulation properties of the gutta-percha, the strength of various outer coverings, how heat affects the insulator, the electrical properties of conducting and insulating materials, conduction, induction, and retardation phenomena, methods of electrical measurement, and ways to measure specific resistance and inductive capacity. So these would all prove to be important things. One important contribution from Siemens Brothers, another London-based cable company formed as an offshoot of the German company, was their recording of measurements of the resistivity of both copper and gutta percha on the same scale. This showed that their values differ by about 20 orders of magnitude. As William Thomson put it, the distinction between conductors and insulators is not an absolute distinction, but a distinction of degree. So here's an important conclusion. Everything will conduct electricity to some degree, and it's important to know what the difference is. Bruce Hunt also highlights this statement in his book, and he notes that this insight that all material substances should ultimately be regarded as conducting dielectrics lay at the heart of Faraday's approach to electrical phenomena and would later be central to Maxwell's theory of the electromagnetic field. So now they're getting interested in field theory. This report on a technical failure was the first of its kind in any industry, and Bruce Hunt concludes that the investigation and subsequent report would help set the course of British work not just in submarine telegraphy, but in much of electrical science for decades to come. It cleared away the rubble of past failures and helped lay the scientific and engineering foundation on which the future success of submarine telegraphy could be built. I'll just show two examples of the importance of the evidence provided to the committee, and we'll look at Fleming Jenkin and Latimer Clark. And notice that these are mostly young guys. They were in their 20s when they got started on this, and they just kept going. Fleming Jenkins had worked on cable laying with Newall, the manufacturer of half the 1857 cable, and he began a collaboration with William Thomson in 1859. In his testimony to the committee, he noted that he had verified Thomson's theory of signal propagation through an insulated conductor, and he stressed the importance for both electrical science and telegraphy of an agreed unit of resistance. So before this, they knew about resistance, and Ohm's law was in effect, but they didn't have a unit for resistance. They would say a voltage of two Daniell cells in series or whatever. They didn't have a unit they could use for interchanging information. Latimer Clark also published text of his report to the committee, over 70,000 words on experimental investigation of the laws which govern the propagation of the electric current in long submarine telegraph cables. In it, he clarified basic terms in common use, such as quantity and tension for voltage and resistance, showing how Ohm's law defined their relationship. He too emphasized the need for the accurate measurement of resistance, as well as the importance of reducing the effects of retardation. His studies of the propagation of electric currents along submarine cables led him to investigate how electric and magnetic forces vary through time and space. Again, this directly pointed the importance of field theory. It's clear from the report that the accurate measurement of resistance was considered to be essential for almost every aspect of cable design and manufacture and for fault finding. This required a defined unit and precise reference standards. Calibrated resistance coils were in use by the late 1850s, but there wasn't yet a defined unit of resistance to provide consistency and repeatability of measurements, and nominally identical coils often had different values when compared on a Wheatstone bridge. What was needed was a precise definition and standard of what came to be called the ohm. So in September 1861, at a meeting in Manchester of the British Association, the Committee on Standards of Electrical Resistance was formed by popular demand. At about the same time, in the summer of 1861, Maxwell was working on measuring electric and magnetic constants to calculate the speed at which electromagnetic disturbances would propagate. So another concept here. We know about the electric field and how fast does it propagate. Members of the Standards Committee included initially William Thomson, Fleming Jenkin, Wheatstone, Maxwell, and other physicists and cable engineers were added later. Working together, and in 1862 expanding their mandate beyond just resistance, over the next few years they created the system of amps, volts, and ohms that has been in use ever since. However, the process was not simple. Units such as the ohm can be defined in either of two ways. The first is by reference to the physical properties of an object whose form can be precisely described. For example, in 1860, Werner Siemens proposed a unit based on the resistance at a temperature of 0 degrees Celsius of a tube of pure mercury 1 meter long and 1 square millimeter in section. This would be convenient for practical use, as its value would be equal to the resistance of a few hundred feet of copper wire. Also, anybody could build one of these. The other possibility is an absolute system. such as one proposed by the German physicist Wilhelm Weber in 1851. This is a rather complex concept based on units of force and motion, which I won't attempt to describe here, but from it, one could derive a universal physical constant roughly equal to the speed of light. And this later proved important in Thomson's theory of telegraphic propagation and in Maxwell's theory of the electromagnetic field. However, this method is not at all intuitive, and it had very little appeal to the telegraph engineers who would have to use it, and who, of course, were on the committee doing the standardization. So the committee determined to devise a system that worked for both telegraphists and lab researchers. But a year later, Fleming Jenkin had to apologize to the British Association for not having completed the work in a single year, so it's proving a little more difficult. Eventually, they decided on an absolute system and voted unanimously to base it on the French metrical system, a decision that would result in wide success of the British Association system of electrical units. But it wasn't until 1865 that the unit of resistance was named the ohmad, soon shortened to ohm, and the same year, official standard resistance coils were offered for sale at £2.10, about $12 at the time. In 1861, the Atlantic Telegraph Company had been greatly encouraged by the conclusions of the Joint Committee, and they began planning another attempt to lay an Atlantic cable based on all of that new information and new technology. This project was delayed by the Civil War in America and by a recession in Britain, and it was not until 1865 that funds were raised and work could begin. Measurements on the 1865 cable were made using both the Siemens Mercury standard and the British Association's resistance coil. But after the success of the 1866 Atlantic cable, the ohm was adopted by the British cable companies, and its use soon spread in the rapid expansion of the cable network worldwide. So the cable network is now propagating electrical standards around the world. It took a little long for other units, but by 1873, the British Association defined the volt and the farad, although it took them until 1881 to define the ampere formally. One important part of the story remains to be told: the derivation of Maxwell's equations, if you're wondering when I would ever get to that. And this shows Maxwell's equations, but this was not the form that he first wrote them in. This is how they're known today, and how they were rendered a little bit later, which I'll also describe. But as we say, the equations were not first as straightforward as they appear to be here. So we've seen that even in the early days of undersea cables in the 1850s, Latimer Clark and William Thompson had determined that the propagation of an electrical signal through an insulated wire was not so simple as putting a current in at one end and receiving it at the other. This was emphasized by what they called the induction of the current on a cable, caused by the relationship between the conductor and its dielectric, which resulted in the retardation of the signal. As I mentioned earlier, Thompson had corresponded with Maxwell in 1854, and Maxwell then became interested in field theory and wrote his first paper on the subject the following year, and he was just 24 years old at this point. He subsequently published papers on lines of electric and magnetic force in 1856, and on his electromagnetic theory of light in 1861-62. Between 1802 and 1864, Maxwell worked closely with Fleming Jenkin and the telegraph engineers on the Standards Committee, where in the course of examining the absolute method of defining the ohm, he hoped to obtain measurements of the relationship between electrostatic and electromagnetic units that would confirm his theory that the ratio of these units was equal to the speed of light. And he wrote a paper on this called A Dynamical Theory of the Electromagnetic Field, in which he formulated a set of electromagnetic field equations, including a fully electromagnetic theory of light. His approach to this had been influenced by the practical nature of the work he had done with Jenkin and the telegraph engineers. The equations in this paper later became known as Maxwell's equations, and they were formally published in his two-volume book, A Treatise on Electricity and Magnetism, in 1873, although they were still not in the form that we know today at this point. Meanwhile, the successful completion of two Atlantic cables in the summer of 1866 had resulted in a very profitable business for the Atlantic Telegraph Company and for other companies, who soon began laying their own cables on the Atlantic route. Also, Britain was looking at the rest of the world. India being a very important trade partner with Britain, John Pender, who had been largely responsible for arranging the funding on the early Atlantic cables, laid a cable to India in the early 1870s, and on this he based step by step a widespread network around the world over the next decades. This rapid expansion of the cable industry meant that it was no longer sufficient to have a small number of technical staff, many of them self-taught, to manage the design, manufacture, installation, and operation of complex cable systems for many different companies. In 1865, Fleming Jenkin noted that we've now reached a point where we look back with surprise at the rough and ready means by which the great discoveries were made on which all our work is founded. In other words, we've been winging it for 15 years. William Thomson had been a pioneer of teaching practical physics, having set up a research lab at Glasgow University in 1855. Although this was initially for his own use, his students assisted in his investigations on the purity of copper for submarine cables, and 2 of his students sailed on the 1858 Atlantic Cable Expedition with him, and others followed into the cable industry. By the late 1860s, rather than just teaching electrical theory, British universities saw the need for education in the practical aspects of electricity, and laboratories were established at University College London and the University of Edinburgh, both modelled on Thomson's lab at Glasgow, and others followed. In 1872, William Thomson told his sister-in-law, "There is quite an epidemic among the lab students to become telegraph engineers." Maxwell himself had retained his interest in telegraphy, and in fact, he joined the Society of Telegraph Engineers, which was formed by the cable guys, and is now the IET, the British equivalent of the IEEE here, the Institute of Engineering and Technology. And on his application, he was promoted by William Siemens as an eminent in science person. So this was high praise from Siemens. And as we see, Maxwell himself had retained his interest in telegraphy. And in 1873, he supervised the establishment of the new Cavendish Lab at Cambridge University with a focus on precision measurements. And also in 1873, he was elected as a full member of the Society of Telegraph Engineers. And at the Society, he helped their efforts to promote accurate electrical measurements. The creation of the laboratory was effectively the beginning of formal electrical engineering courses at British universities. Bruce Hunt notes that these laboratories emphasized mastery of the techniques of precision electrical measurement, and they turned out substantial numbers of students equipped to work in cable company testing rooms or to teach those who would. And the specialized needs of cable testing and repair led to the development of many new instruments. To mention just a few, William Thomson's mirror galvanometer and siphon recorder, paper tape hand punches, automatic transmitters, calibrated resistance coils, and a variety of keys for testing and measuring the discharge characteristics of submarine cables. And here we see on the left a cable transmitter, which working on tape punch by hand would send the positive and negative signals, which were the only way to work long cables. And that was clockwork driven, I believe, initially. And then on the right is a siphon recorder, which takes a similar mechanism to the mirror galvanometer, but uses a little inkjet through a glass siphon tube to spray the ink onto the paper tape, because the friction of the tape on the glass, if the glass were to write directly on the tape, would stop it moving. So here you've got a wavy line above and below the center line showing dots on the top and dashes on the bottom, equal length pulses, of course. And these inventions of William Thomson, as I said, he licensed the cable companies and became very, very wealthy as a result. So John Pender, who had founded the Eastern Telegraph Company to send a cable to India, established his own training school at the cable station in Porthcurno, Cornwall, and cable men educated there were sent to stations all over the world. And the Eastern Telegraph Company in 1930 merged with Marconi's wireless interest to form Cable and Wireless, and they used Porthcurno as the cable terminus, and that was also their training school, and that remained in operation until the 1960s, and the site is now a museum with the station virtually as it was when it was closed, and well worth a visit if you happen to be in the bottom left-hand corner of England. And if we look into the future a minute, we find a 3-volume hardcover set of books titled Telegraph Cable Engineering, and these were privately published by the Eastern Telegraph Company in the 1920s for the reference of their staff at cable stations worldwide. And perhaps to give you an idea of the complexity of cable technology, note that these 3 books have a combined total of over 2,000 densely packed pages containing all the information, theoretical and practical, that staff would need, especially at a remote station where they couldn't call home for help. We're getting near the end now, and I'll end with some final words on Maxwell's equations. In 1873, as I mentioned, the original complex set of equations was published in his treatise, the culmination of his work on field theory. And important as they were, the equations in this form would probably have remained at least somewhat obscure. but they lead to one final connection that will complete our story of the intersection of theoretical physics and the practical needs of cable companies. This thing is Oliver Heaviside. Born in 1850 at the very beginning of undersea cable communication, Heaviside was a nephew by marriage to Charles Wheatstone, co-inventor in Britain of the first commercially successful landline telegraph, and in 1867, his uncle sent him to work as an operator at a telegraph company in Newcastle, managed by Charles Wheatstone's brother. As I said, everybody knew everybody. 2 years later, Heaviside took a job with the Great Northern Telegraph Company, for whom British contractors were laying a cable from Newcastle to Denmark, and he was soon promoted to electrician, the highest technical rank. While working on cables, Heaviside, on the left there, had come across Maxwell's treatise not long after its publication in 1873, when he again was in his early 20s. He was self-taught in mathematics and physics, and he found the equations heavy-going, as did most readers, but he recognized the great importance of the work. As he said later, it took him several years to understand as much as I possibly could about Maxwell's work. He continued with his own research and helped develop transmission line theory, then known as the telegrapher's equations, which he wrote about in 1876. He continued this line of work for the next 7 or 8 years, during which time he researched the skin effect and patented the coaxial cable. But he also continued to think about Maxwell. In 1884, Heaviside returned to the study of Maxwell's equations. In order to simplify them, of course, he invented a new technique for solving differential equations and independently developed vector calculus. Using these new mathematical tools, he was able to reduce 12 of the 20 original equations to just 4 differential equations with 2 unknowns. The 4 equations describe the nature of electric charges, moving or static, magnetic fields, and the relationship between the two. In other words, everything you need to know about how electromagnetic fields work. James Clerk Maxwell died in 1879, aged just 48, but his field theory and the associated equations were key developments of the 1800s. And in Edinburgh, where Maxwell was from, there is a statue, a bronze statue, and this plaque is set into the sidewalk there to commemorate his great work. This is near the statue of him on George Street in Edinburgh. As I mentioned, his equations and the field theory were key developments of the 1800s, and they formed the basis for many aspects of modern physics, including the understanding of communication technology, from telegraph cables to radio to fiber optics. And so the importance of the practical requirements of the cable telegraph industry to the foundation of field theory cannot be overstated. One final note goes to Albert Einstein, who on the centenary of Maxwell's birth in 1931 described Maxwell's work as the most profound and the most fruitful that physics has experienced since the time of Newton. Heaviside himself made many contributions to electrical practice and theory, among them his suggestion in 1902 that there must be a reflective layer in the ionosphere which would explain SKIP, the observed propagation of radio waves beyond the horizon. This layer, of course, was later named for him. So this has been a complex story in which I've touched only the highlights of the many advances in cable technology and electrical theory in the second half of the 19th century. And I'll close with saying it's remarkable to think that the collaboration of the cable engineers and the scientists took just 23 years to go from Ohm's law in 1850, when the first cable was laid, to the definitions of the standard units beginning in 1861, then to Maxwell's equations in 1873, when he published the equation in their original form. This was then the foundation of pretty well all the major developments of communications and other things in the 20th century. And thank you for listening so intently for an hour. That's the end of my talk.